Okay, let's start class in 3, 2, 1. Good morning!
Good morning!
Hi everybody, my name is Mr. Broder. Welcome to 9th grade science. Here's what we're doing today. We are going back and looking at do you remember when we made those gas tubes? Yeah?
Yeah.
Like, what did we see in those gas tubes? Shout it out. Like, what happened?
Colors.
We saw colors and stuff. Lee, you're going to be like so loud on that because you're talking right to it. We got colors, we got weird colors. We saw that the different elements made different colors, which was bizarre. Did we get like smooth, spread out colors, or were they really particular colors?
Particular colors.
Like really particular colors only, right? Okay, so we're going to look today at like why that happened. In doing that, I'm going to explain how light works, and then we'll move on to use that to understand how electrons work. Okay? So first off, let's review. What particles, shout it out when you know the answer. What two particles are in the center of the atom's nucleus? Shout it out.
Proton, neutron.
Yeah, protons and neutrons are in the middle. And then what particles are going to be like whizzing around the outside there?
Electrons.
Electrons. Okay, just quick review. We just needed to like get our head back around that. So we'll look at light, okay? Did we look at light already? Okay. So light is, it's a type of energy. Get this note down if you don't have it already. Light is a type of energy. It's produced when electrons move between electron shells. Light is one part, don't erase it if you have something, we're just going to add to it. Light is one part of the electromagnetic spectrum. Yes, I want you taking notes. Is there notes?
No, did we get this last class?
I don't know, you should go check.
Yeah, we did.
So light is one part of the electromagnetic spectrum. It's produced by electrons moving between shells. Shells are going to be like the energy levels of the elements. We'll look at that in a minute. Okay, let's start. So like, what is light? You've heard of visible light, right? But we're just going to, did we watch this video last class?
No.
Okay,
Oh, so
excellent.
you already left.
Light is a strange thing. It isn't just what we can see. Light can be broken up into different types, and we call the whole family the electromagnetic spectrum. So even when it's dark, light is still all around us. Light can be created by making an electron oscillate. This creates an oscillating magnetic field and an oscillating electric field, which we call an electromagnetic wave or light. We often represent light as a wave. Just like water waves, light has a wavelength, a frequency, and a speed. The different colours of optical light have different wavelengths, and so does the rest of the electromagnetic spectrum. Gamma rays are the most energetic, whereas radio waves have the least energy. Even so, light is the fastest thing in the universe. In a vacuum, all light waves, even radio waves, travel at an incredible speed of 300 million meters per second. The Royal Observatory is overrun with squirrels. They're hard to miss during the day because they reflect visible light from the sun, but at night it's more difficult. However, they do emit infrared light, and if our eyes could detect it, we would be able to see them in the dark. If we pass high-energy X-rays through them, the squirrels look very different. Humankind has invented lots of different instruments to show us what our eyes can't see, like our Great Equatorial Telescope, which captures huge amounts of light and allows us to see objects that are tens of millions of trillions of kilometers away. We can see matter interact with light and change it. The gases in the Earth's atmosphere scatter blue wavelengths of sunlight, giving us blue skies during the day and red skies at sunrise and sunset. We can watch sunlight reflect off planets and the moon. During a lunar eclipse, red sunlight changes direction as it passes through the Earth's atmosphere and reaches the moon. And although visible light from stars can be absorbed by dust in space, we can detect the infrared light, which gets through to see baby stars hiding in nebulae. Light can even appear to stretch out. Since our universe is expanding and galaxies are moving away from each other, the light they emit is stretched to longer wavelengths. We call this redshift. Some galaxies are so far away that their light has shifted and stretched from visible to infrared, so we can no longer see them. Stranger still, the universe has unknown amounts of dark matter and bizarre black holes, so even if we can detect all the different types of light, there are still some things in the universe that will remain invisible to us.
Okay, that goes deep, like very quickly. So let's get some basics down. So what is a photon? Well, photon is like It's one little particle of light. It's not exactly a particle, but it sort of is. It's a wave packet. There, you got a note on photon. A photon is it's what we call a particle of light. Technically, it's just energy. It's a little wave packet, but it can sometimes act like a particle. Like, if you want to think of like one sunbeam, one little tiny bit of sunlight, that's a photon. Yeah, it's bizarre. It's a wave packet. Photons, light in general, does not behave like anything else. It behaves like light because it is light. It's very hard to make analogies for it without being like inaccurate, but I'll do my best.
Oh, no.
So you get a photon of light as a particle of light. Have we talked about where electromagnetic radiation comes from? We did. Electromagnetic light comes from electrons moving, or you could say, the other way you could say electromagnetic comes from a moving or oscillating charged particle. So there's your next note. Electromagnetic radiation comes from moving charged particles. Or if you want to say oscillating charged particles is like a more scientific way to say moving. You could also say energized charged particles can make light. All of these are different things that can make a photon. If you have an oscillating or a moving or a vibrating charged particle. When I say charged particle, charged, like it has a positive or negative charge, what part of the electron, sorry, I just said it, what part of the atom has a charge on it?
Protons.
Protons and electrons, right? And which one of those is like free to like move around more? Yeah, so the electrons that are vibrating around the atom are going to be the parts that can give off photons most readily. Protons can do it sometimes too, but we're gonna like experience and talk more about the light coming off of electrons. Okay, got it. Let's talk about like the colors of light. What makes different colors of light? Why is red light red, blue light blue? Any guesses?
Red, blue light, blue.
Yeah, it's actually the wavelength. The real answer is it's the wavelength. Red light has a longer wavelength. The blue light has a shorter wavelength. That's why it looks that way to us. That's the only reason. Science better. I think so. Is Kylie Peterson here today? Okay, bye.
So we can.
So we got different colors are caused by different wavelengths of light. I'm not talking about pigments. I'm not talking about dyes and pigments. I know those are different, right? Like how you mix paint, that's different. I'm talking about light. Light makes color by doing this. So if a wavelength of this length, it happens to be like 700 nanometers, or maybe 665 nanometers. If a wavelength of light of that length hits your eye, it looks red to you. If the wavelength is shorter, like let's say it's in the 470 nanometer wavelength, it hits your eye, it looks blue. If it's shorter still, if it's like shorter than 400, if it's like 300 nanometers, your eye will not see it. That wavelength just hits your eye, and there's nothing on your retina that can sense that. And that would actually happen to be ultraviolet, so it just hits your eye. And we'll talk about sometimes ultraviolet can start to be dangerous.
So it's purple.
If it's longer than this red, if it's like 750 nanometers, or bigger than 700, it can hit your eye, and your eye just can't see it. That would be like infrared, which you've actually like felt infrared heat before. You've been to like Sbarro's or like those places where they have like the orange lamps that keep your food hot. You ever put your hand under one of those? Yeah, like the light's not very bright, right? It's kind of like a dull orange, but you put your hand under it, you're like, whoa, like it's really warm. That's because it's shining a lot of infrared light. The wavelength is too long for your eye to see. There's a ton of light shining, it's just infrared.
So which one's faster, purple or red?
Light all travels at the same speed, which is the speed of light. Good, interesting question. They travel at the speed of light, which is in a vacuum. And that's like, I have to be particular, I'm saying in a vacuum. They will all travel at the same speed, which is like the fastest speed possible. It's really, 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 really fast. Now, there is some difference about them. Oh, hey, let's just like fill up the note sheet though. All the colors. If you have all the colors together and you shine them in one spot, what color does that look like? Yeah, there you go. You got your notes. All the colors of the rainbow together produce white light. That's what white light is. It's all the colors mixed together. pausing so you can get your notes written down. All the colors together, like white light. How do we know that white light is white light?
Because we mixed all the colors together.
Can you think of like one little tool that's often made of glass? A prism. Have you heard of a prism?
Yeah.
It's a little glass. They can be different shapes, but
Everyone
they're like a little glass prism. We get white light coming in, and then boom, the rainbow comes out the other side. You can do the opposite too. You can take a rainbow, shine it into a prism, and then you get white light out. You can also take like 5 spotlights of all the different colors and just shine the spotlights, like colored spotlights, onto one spot, and that spot on the ground will be white. It's kind of cool. It's a fun little experiment. My projector. This projector shines actually only 3 colors. It can shine blue, greens, and red. But by carefully mixing how much of each, it produces, our eyes interpret it as the other colors, which is kind of cool. So like this right here is white because it's getting shined both red and blue and green. And then our eye is like, oh, it's white. Okay, that's cool.